Hello and welcome. My name is Michelle Brasso. I'm a 9 through 12 science educator specializing in physics and astronomy. And if you've seen these around your department and they give you a little fright, no need to worry. This session is for teachers who are new to the incredible power of the dynamics cart. This really is dynamic. It's the powerhouse of your physics department. These little guys can do so much science. So I want you not to be afraid of them. This session is designed to take you from where you are, introducing you to some of the great, easily accessible demos, labs, and activities that you can do with dynamics carts. For reference, I'm using PASCO Smart Carts as well as PASCO SPARKvue software, which is free for students to use on Chromebooks and on their devices. Some features of your dynamics cart include the power button and the charging port, as well as the accessory port, a tray for slotted masses and accessories, a spring-loaded launcher with 3 different settings, a Velcro side for carts to connect together in completely inelastic collisions, as well as a series of attachments on the other side. This is where the force sensor is. So you've got the option of adding in a hook that can be useful with some string or elastic bands, a rubber bumper, or a magnetic bumper with the pin to make sure it's added in on the right side for some magnetic repulsion between the carts. Let's start exploring what we can do with these dynamics carts. First, let's set up an experiment in which students are exploring position time and velocity time graphs. We'll start a new experiment. And let's choose some graphs that will be side by side. In terms of connecting the cart, you'll need to click on the Bluetooth button. And then each cart has a number on it, and you'll be looking for that number when you connect your cart. The range of the Bluetooth is about 10 meters, so students on one side of your classroom could theoretically connect to the carts on the other side of the classroom. So make sure your students are using the appropriate number. Once we're connected, we can select what measurements we want. So starting off here, you may want to use position time and velocity time graphs. And I'm just going to zero the sensor now. I must have been moving it. And now we can start moving this dynamics cart and plotting out its position and its velocity side by side. Students will have fun with this. So it is starting, so in this direction, and this direction. We'll just have a lot of fun with this. And the challenge could be bring your cart back to a 0 displacement. So now we're back at the starting point. We've got 0 velocity right now. We can have acceleration. We can try to maintain a constant speed. We can decelerate. And your students can explore these different shapes. When your students are all done collecting data, they just hit the stop button, and there they have all of their data. Here you can use the 4 arrows outwards to better fit the data to the screen. And there's a crosshair that allows you to select points. So if students need to find the specific time and position, then they can find the same over here on their velocity time graph to pull those up. If they want to try again, they can just hit start. And they've got their dynamics carts ready. It hides the previous trial, and we can do something like accelerate and see what that graph looks like. We can have it go slowly. We can have it have a positive or negative velocity. And if that's ever backwards from what your students prefer, then just stop this, and we can pull down here to change sign. And that just flips what was positive is now negative and vice versa. So when you're getting started with these types of graphs, it's really fun to get these carts out and have your students explore. In that way, they start building their understanding of how the program works as well in a low-risk setting. Later on in the unit, your students may want to compare velocity time graphs to acceleration time graphs. So we can do the same here. It is ready to go. So we'll click start and we'll give this an acceleration. And we can go the other way. And see what happens on the graph. Now, this is going to be best used with small accelerations, small velocities. Of course, there is a larger track that you can use as well. When teaching Newton's laws, you can have the students use the carts on or off the track to demonstrate all three laws. For example, Newton's first law: an object at rest stays at rest unless an unbalanced force is acted upon it. There it is. They can also show how the cart moves when a force is applied to it. And they can start getting creative with Newton's second law. For example, students can give the cart a push and observe its motion, and then try that again with the same amount of force and more mass. Less acceleration there, even more mass. And with that same push, they can demonstrate this really more qualitatively than quantitatively, but it goes far for them to cement those concepts of Newton's second law. Newton's third law can also be shown with two carts with the hook attachment and an elastic band. When the students stretch the elastic band not too far, they'll be able to see on their screen the equal and opposite forces acting on each of those dynamic carts. My favorite and the students' favorites activity with using these smart carts is to get them to smash together. So in the lab provided, your students will get to explore inelastic, completely inelastic, and elastic collisions with their dynamics carts. To set this up, students will need to have two graphs, and they will need to have the velocity of both the blue and the red car. I find that this activity works best when the carts have unequal masses. So we'll add in a couple of masses onto one of the dynamics carts, and then we're going to smash them together. Students can start a trial in which they send one cart towards the other, or you can have both carts come in together. I find that using the shorter tracks, I like to have both carts coming in together, and that gives both of the carts an initial velocity. It's a little bit easier if one cart is stationary, but then students need to make sure that they've got the stoppers or they prevent the car from flying off the track. So here we go. And they can see the big difference in the final velocity of the two carts. So we'll stop that. And they can use this tool to optimize what they see on the screen. And it's the student's responsibility to then select those key points of where the collision occurred. So from there, they'll grab the initial and final velocity right before and right after the collision is over. After that trial, all we have to do is keep the same mass, but turn the two carts around so that now the Velcro sides are facing one another. And again, we start. And stop. For the last trial, students need to be a bit more light-handed because we're going to attach the magnetic bumpers. These will change the overall mass of the cart, so students need to remass both. turning these cards both inwards and being gentle, we can see the magnetic repulsion. And what a collision that was. Students will use the data, the initial and final velocity of both cards, to determine whether the total kinetic energy was conserved throughout the experiment. They'll do that 3 times, once for the experiment with the magnetic bumpers, once for the plastic or rubber bumpers, and once for the Velcro experiment. Using that data from the kinetic energy, they'll be able to determine whether the collision was elastic, inelastic, or completely inelastic. They should, however, already know that when the 2 cards stick together, we have the greatest loss in kinetic energy, so that's going to be a completely inelastic collision. After that, you can extend this with an analysis of the final and initial velocities and calculating the momenta. Here, the direction does matter, so students will need to make sure that they do record the positive and negative signs on their velocity data. In a similar way, how we were working with collisions, we can also work with explosions. So we can use these spring-loaded plungers for these carts to explode off of one another. Here we go. So students can see the changes in the velocity as these 2 explode off of one another. Now the plunger has different settings, so the more pushback it is, the more it's going to explode. And then if we just do the first setting, you'll see it doesn't explode as much. Now what can be really fun for this explosions is by changing up the masses. So if we add mass to one of the cards, the students can predict and explain what they think will happen, and then after they observe, they can explain again what actually happened. So here we go. Unequal masses. This is also great for circling back into Newton's second and third laws. If we have really unequal masses, we're going to see a big difference in how these cards move. Dynamics cards are excellent when working with frictional surfaces. They themselves have very low friction between themselves and the track, so instead we can use these little sleds that can attach to either the hook via string, or they attach directly to the tray. And then we can pull this to demonstrate friction. My goal when doing this experiment is to get that beautiful friction curve. So showing static friction increasing to the point of when static friction is overcome and it changes to kinetic friction. So there are different surfaces on the bottom of these sleds, and if we were to pull the sled, we'll find that very quickly it moves. So that doesn't give us much excitement or insight into static friction. This experiment works best when the mass is really heavy in the sled, so that students have to be not as fine as if there was very little mass in here. So let's try this. I'm pulling, oh, almost had it there. Oh, that's actually pretty good. One more time. We're pulling, and then it finally starts to move. Can let it stop. So we'll gently pull, trying to increase gently until there it was, the cart finally moved. There it goes. And you'll see that sudden drop right here when the cart starts to move. So that's when we start getting into kinetic friction. This part of the graph here is what I want the students to focus on. I want them to see that the force of static friction grows and grows with the applied force to a certain point. When they do calculations and they're not thinking, they might assume that that force of static friction is the maximum force of static friction because that's what the calculations show. No, that force of friction grows with the applied force to a point. So I find this activity really helpful for clarifying that misconception. Taking this further, they can calculate the coefficient of kinetic friction by slowly applying a steady force and then using the mass of all of this to determine the value of mu. You can also show centripetal force with the dynamics carts by tying a sturdy string with many knots on one end and having a student grab onto the other. They can change the radius of their spin. I like to do this one outside on the soccer field. Students spin this around and they can try different things like spinning it faster or spinning it with a smaller radius to really get an understanding of the centripetal force equation. With goggles on, this ballistic launcher is a lot of fun in class for a great demonstration. What it is a ball with a plunger that can be plunged down, and then there's a timed release. And there it goes. So it does need to be calibrated depending on your surfaces. So there are some left and right adjustments to make this land perfectly back in the catcher. So I recommend calibrating that first, and then you can attach it to the smart card. So let's calibrate. Takes a little trial and error, but then we get it perfectly. All right, so now that we have this, we are going to attach it to With this, the students can see the independence of the X and Y directions when it comes to velocity. This is a great demonstration for showing projectile motion with the dynamics cards, but make sure you're wearing your safety goggles. Thank you for being here with me today to learn about the powerhouse that is the dynamics cart. My hope is that you'll be able to use them now and keep them from collecting dust in your prep room. They really are fantastic for learning lots of physics concepts. This was just the beginning. There are so many other experiments that you can do with the dynamics carts, so I invite you to explore those and try these with your students. I hope that you enjoy it. Thank you.